Hey Chem 20s, hope you're all safe and well. Here is Chapter 4.3 in Gas Laws, and we're taking a look at a concept on molar volume. So for this one here, we're building upon Avogadro's theory and ideas from the last section in 4.2, where he said that if you were going to measure a volume of gas, then that volume of gas that you are measuring, however many liters or milliliters it might be, is really just a measurement of the empty space between the particles. This meant that any gas could be very easily compared to any other gas. It also allowed us a way in to figure out the mole quantity. Remember all those Skittles we used to talk about. So what we're going to do now is just reinforce one of the ideas that we brought up in that particular section on molar volume. This is just a conversion. This is something we're going to be able to use later. It's very much like molar mass. All right, it's a very, very simple idea that we get to utilize, and it's a nice, useful conversion that allows us to move between the moles that we need for chemistry and one of the many things that we can measure in lab that isn't just trying to count an infinite number of particles. So please remember the mole concept. A mole is just a count. It's no different than, let's say, when we mention things like a dozen or a fortnight or things like that, or horsepower. It's just a name we give to a quantity. So a mole is this many particles. In this particular unit, all right, this is the number of gas molecules or atoms. Okay, so for here and for this unit, we're just talking about those little gas particles. Avogadro told us in section 4.2 that any equal volumes of a gas would happen if the temperature and pressure remained the same. This meant that if I had 5 liters of oxygen, I would have the same number of oxygen particles or molecules if I had 5 liters of nitrogen or 5 liters of ammonia or 5 liters of methane. It would all be the same because the particles of a gas are so infinitesimally small compared to those huge spaces between them that they are all directly comparable. So this makes gases actually quite easy to work with and measure so long as we can keep temperature and pressure identical between them. So it gives us this concept of a molar volume. The volume that 1 mole of any gas will occupy at a set temperature and pressure is known as a molar volume. Now this is a nice easy shortcut for us, and 2 numbers that you'll probably end up memorizing with just a couple of examples, but they are on your data sheet as well. The first one is at STP. Remember, this is at 0 degrees and 101 kilopascals. But if I give you 1 mole, this many gas particles, of any gas, it always occupies 22.4 liters. So therefore, we have 1 at STP. We get 22.4 liters per mole. Okay, this means that if I give you 1 mole of oxygen at STP, it occupies a balloon that is 22.4 liters large. If I give you 1 mole of ammonia gas at STP, it occupies a canister 22.4 liters big. For SATP, which is slightly warmer, means the particle will have much more energy and even slightly lesser pressure, all right, 25 degrees C and 100 kilopascals, we see that 1 mole of the gas occupies a slightly larger space. So at SATP, this becomes a slightly larger value. Okay, and we see both sets of conditions quite regularly and quite easily. So within the picture, as we take a look at it, you can see it does not matter what gas we have. This one is helium, this one is oxygen, this one is nitrogen. Okay, with 1 atmosphere of pressure, which is at STP, and that particular temperature of 0 degrees, shown by the low temperature, 273 Kelvin. All right, 22.4 liters represents the same volume for each individual gas. Important part to remember, they would all have different weights. because molar mass is a different measurement and a different quantity. Okay, so now we have two different ways to move between moles of a substance and one of the things that we can measure in lab. In Chem 10 and early parts of our review, we got into molar mass, which was just a conversion between the moles of a substance you put on the scale and the gram weight that it would read. In this case, gases would be very difficult to put on a scale, so we have a way to measure out the amount of particles based upon the size of the balloon or the amount of volume that we have. I hope that makes sense to you. Let's take a look at a couple of examples. All right, we're going to build upon that factor label method that we've been using once we introduced Avogadro. So look, we have 5 moles of a gas at STP. Think critically about this for a moment. If 1 mole is 22.4 liters, then how big of a balloon would you need to hold 5 moles of this gas? It would obviously have to be 5 times larger. So let's look at what the conversion does for us. We used factor label when we used molar mass. It's going to be the great strategy that we'll use here for dealing with molar volume. Okay, so start with 5 moles of your gas. But I don't want moles. I want volume in liters. So moles will go on the bottom. Now at STP, what is the fraction between moles and liters? Well, we just talked about that. At STP, it's 22.4 liters for every mole. So we can use that here. 22.4 liters of any gas per mole quantity. Moles now cancel because they're on top and bottom of my fraction, and now it just becomes 5 times 22.4. The same math we were really just thinking about a moment ago. And so, run that through your calculator, and your calculator spits out 112 liters, and lo and behold, your calculator for the first time in a long time actually told you the right answer, because that is the correct answer in sig digs. Let's get one more into this video, and we'll get the other examples out of the way in part 2. Here you have 3.50 moles of gas at SATP. All right, well, we have a quantity, 3.50 moles. I don't want moles, however. I want liters. And so we had said, at the slightly warmer conditions and lower pressure of SATP, the volume, that 1 mole of gas, would be a slightly different volume, and so we would have a balloon that was 24.8 liters large. All right, look at your math, the moles cancel, and this one works out to 86.8 liters. When that cancels out, 24.8 liters per mole, so if I have 3.5 times more moles, I should have 3.5 times more volume. Okay, there you go. There's your correct sig dig answers. Try a little bit of examples 3, 4, and 5 on the next page, maybe before you look at the next video, and then take a look at it and see how you did. All that's in there is a bunch of different conversions. Okay, see you in part 2 of 4.3 lesson 1 in the next vid. Good luck, guys.